Welcome to the deep dive. We've got, well, a really fascinating source today, a classic.
Absolutely. We're tackling a cornerstone of physics teaching.
That's right, the Feynman lectures on physics. Specifically, we're zeroing in on just one chapter today. Chapter 18, rotation in two dimensions.
Really important one.
It really is. Up to now, in the lectures, things have mostly been treated as points, right? Simple particles.
Yeah, point mechanics, much simpler.
But the real world,
Yeah.
it's messy. Things have size, they spin, they wobble. So our mission today is to unpack the tools Feynman gives us here.
Tools like center of mass, torque, angular momentum.
Exactly. And the moment of inertia. We want to show you how these concepts make sense of complicated spinning objects without getting lost in the super heavy math.
And what's so great about Feynman's approach here is seeing how these seemingly new ideas for rotation, they actually just flow naturally from Newton's laws.
Ah, right, if you look at it the right way.
Precisely. This chapter gives us what he calls the first theorem about complicated objects. It's about finding the simplicity hidden in complex motion.
Okay, great. So let's start with that foundation, the concept that helps simplify things right away. The center of mass.
Sounds good.
Okay, so picture this. You throw some, I don't know, weirdly shaped piece of wood in the air.
Yeah, something tumbling end over end.
Exactly. Spinning, wobbling. If you tried to track every single point on it, you'd get this incredibly complex tangle of lines.
Utter chaos visually.
But Feynman points out there's always one special point, just one. The center of mass, which they label R. And that point, it moves simply. If gravity is the only external force acting on the whole thing, R traces out a perfect, smooth parabola, just like a simple projectile.
And that's the magic, really. Defining it as one thing, it's, the weighted average position of all the mass.
Weighted by how much mass is where.
Right. But the result is the powerful part. The total mass of the object times the acceleration of just that one point, the center of mass. That equals the sum of only the external forces acting on the whole system.
Okay, wait. Only external. So what about forces inside the object? Like people walking on a ship or an engine turning?
Doesn't matter for the center of mass motion. All those internal forces, they come in pairs action-reaction, and they cancel each other out when you sum them up for the whole system.
Newton's third law in action there.
Exactly. So the motion of R is completely unaffected by all the internal wiggling and spinning.
Wow. Okay, so that is a massive simplification tool then.
Huge.
You can take this complex, spinning, maybe even vibrating object, like a satellite or something,
Or yeah, a train full of people moving around inside.
and just treat its overall translational motion as if it were a single particle located right there at R.
It lets you neatly separate the motion of the object through space, its translation.
From the motion around its center, the rotation.
Precisely. Which brings us to describing that rotation.
Right. So if the center of mass handles the straight line, or parabolic movement, we still need to describe the spinning part.
And to make that manageable, Feynman first talks about a rigid body.
Okay, what does that mean exactly?
It's an idealization, basically. It means an object where the distance between any two internal points stays absolutely fixed. It doesn't bend or stretch or wobble.
Got it. So it simplifies the geometry, no changing shapes while it spins.
Exactly. And to describe this rigid rotation, we need angular versions of our familiar linear concepts.
Okay, like analogs.
Right. So instead of linear displacement, $6, we talk about angular displacement, usually delta theta, a change in angle.
And instead of linear velocity, Vedel dollars.
We use angular velocity omega 1, which is just the rate of change of that angle, how fast it's turning, usually in radians per second.
Makes sense. And acceleration.
Same idea. Linear acceleration becomes angular acceleration alpha. That's the rate of change of the angular velocity, omega label.
Okay, so we have this parallel language. But how do they connect? How does the angular speed relate to how fast a point on the object is actually moving linearly?
Oh, that's crucial. Think about a point on the rigid body at a distance $3 from the axis of rotation. When the whole body rotates through a small angle delta theta, that point moves a small linear distance. And the relationship is simple. Its linear speed is just its distance from the axis, $3 times the angular velocity to LIGO.
So, Vedel dollars of omega.
That's the one.
Yeah.
Vedel dollars omega.
Okay, let me visualize that. If you have a spinning wheel.
To the merry-go-round.
Yeah, exactly. Everyone on the merry-go-round has the same angular velocity, omega.
Right.
They all go around in the same amount of time.
Right.
But the person sitting near the edge, with a larger dollar,
They're covering more ground linearly.
right, their linear speed 5 is much higher than someone sitting near the center, closer to the axis.
Even though they rotate through the same angle together, that Vita-Kremega relationship is fundamental for understanding how rotation translates to linear motion for parts of an object.
Okay, that makes a lot of sense. So that's kinematics describing the motion. Now, dynamics, what causes changes in that motion.
Right. If we want to change the rotation, make it spin faster or slower, we need something analogous to force.
A rotational push or pull.
Exactly. And that's torque. We use the Greek letter tau, tau. Torque measures how effective a force is at causing something to rotate. It's the twist.
The twist, I like that. How is it defined? Is it just the force?
Not quite. It's more subtle. Feynman actually introduces it by thinking about the work done by a force during a tiny rotation.
Okay.
But the more common way to think about it, and what he gets to, involves the geometry of where the force is applied.
Ah, like where you push on a door matters?
Precisely. If you push right near the hinges, it's hard to open. Push far from the hinges, near the handle, and it's easy. Same force, different effect.
So it's not just the force magnitude?
No.
Yeah.
It's mathematically defined using a cross product involving the position vector from the axis to where the force is applied and the force vector itself.
Okay, cross product tau xxi way asx in 2D, right?
That's the one. But conceptually, it boils down to something really intuitive. That lever arm principle.
The lever arm. I've heard that.
The torque depends on the distance from the axis, $3, multiplied by only the component of the force that's perpendicular to that radius line.
Ah, so any part of the force pushing straight towards the hinge or pulling straight away?
Does nothing. Zero torque. It only contributes if it has a component trying to move the point around the axis, tangentially.
Okay, so the torque is effectively distance from axis times perpendicular force component.
Exactly. Or you can think of it as the full force magnitude multiplied by the lever arm, which is the perpendicular distance from the axis to the line along which the force acts. Same result.
That's why a longer wrench makes it easier to turn a stubborn bolt. You increase the lever arm.
You got it. Less force needed for the same torque. And this is critical for equilibrium, too.
Equilibrium meaning not moving.
Right. For an object to be in static equilibrium, completely still, not translating and not rotating, two conditions have to be met.
Okay, what are they?
First, the net external force must be zero. That stops translation.
Makes sense.
Second, the net external torque, calculated about any axis you choose, must also be zero. That stops rotation.
Got it. Both forces and torques have to balance out completely.
Exactly.
Okay, so torque is the rotational equivalent of force. Now, you mentioned Newton's second law earlier, y dollars dp/dt2. Force is the rate of change of linear momentum. Is there a rotational version of that? A rotational momentum?
There absolutely is. It's called angular momentum, usually denoted by law dollar.
Angular momentum, okay.
And just like torque is the rotational analog of force, angular momentum dollar is the rotational analog of linear momentum pel dollars.
How is it defined? For a single particle first, maybe?
Yeah, for a single particle, its angular momentum about some origin is defined using its position, $6, and its linear momentum components, EPXTM, VX, PM, EA, specifically law dollar equals XP, Y, 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 pa, Y.
Wait, that looks very similar mathematically to the torque definition, $6 YFST.
It is. That structural similarity is deep. Position crossed with force gives torque. Position crossed with momentum gives angular momentum.
Okay, interesting parallel. So what's the big relationship then? The rotational Newton's second law.
It's exactly what you'd hope. The rate of change of the total angular momentum of a system, dl dt, is equal to the total external torque applied to that system.
So tau dl dt, that's the fundamental law governing how things start spinning, stop spinning, or change their rate of spin.
Wow, okay. That connects everything. So what if the torque is zero?
Well, if tau equals dollars, then del dt equals dollars.
Which means dollars doesn't change.
Exactly. Angular momentum is conserved. If there's no net external twist acting on a system, its total angular momentum stays constant.
Okay, this sounds important, like the conservation of linear momentum or energy.
It is just as fundamental. Think about planets orbiting the sun.
Okay.
The force of gravity pulls the planet directly towards the sun. It acts along the radius line.
Right. No perpendicular component to that force relative to the sun.
Which means the gravitational force exerts zero torque on the planet about the sun.
So tau allows our 6. Which means the planet's angular momentum, $, must be constant throughout its orbit.
And does that explain anything we observe?
It explains Kepler's second law. The law that says a planet sweeps out equal areas in equal times. That's a direct geometric consequence of its angular momentum being conserved.
Whoa. Okay, that's a powerful connection. From tau dLdt to Kepler's laws.
It really is. And this conservation law applies to whole systems too. If the total external torque on a system is zero.
Like maybe two colliding asteroids spinning in space.
Yeah, or skaters pulling their arms in.
Yeah.
The total angular momentum of the system stays constant even if internal forces are rearranging things and causing internal torques.
Why do internal torques not matter for the total L?
Same reason internal forces didn't matter for the center of mass. Internal torques also come in action-reaction pairs between parts of the system, and they cancel out when you sum them all up. Newton's third law again.
Okay, it's all beautifully consistent. So we have this conserved quantity, $1. How do we relate it back to our rigid body spinning with angular velocity to omega?
Good question. We know dollars is conserved if tau 0. But what is dollars for a rigid body? We need to sum up the angular momentum, law dollars heat PPEPI, for all the tiny mass particles miniballs making up the body.
That sounds complicated.
It seems like it would be, but because it's a rigid body, all particles share the same angular velocity omega.
Yep.
When you do the summation, it simplifies beautifully. The total angular momentum dollar turns out to be just law dollars equals I omega.
Okay, wait. We have omega, the angular velocity. What's other dollar?
V dollar is the moment of inertia. This is the final piece of the puzzle for rigid body rotation.
Moment of inertia. What does it represent?
It's the rotational equivalent of mass. Mass tells you how much an object resists changes in its linear motion and inertia. Moment of inertia, a dollar, tells you how much an object resists changes in its rotational motion.
Inertia against turning.
Exactly. Inertia against angular acceleration. How hard is it to get this thing spinning or to stop it once it is spinning? That's determined by a dollar.
And how do we calculate dollars? You said it came from summing things up.
Right. You calculate E dollars by summing up. For every particle molar in the body, its mass multiplied by the square of its perpendicular distance from the axis of rotation. So sum my right to 2.
Okay, sum of Buhrer 2 for all the bits of mass.
Yeah.
That 20 squared, that seems really important.
It's crucial. It means the distribution of mass matters much more than the total mass itself. Mass that's far away from the axis contributes way more to the moment of inertia than mass close to the axis.
Because of the square term. Double the distance, quadruple the contribution to a dollar.
Precisely. So an object with its mass concentrated near the axis will have a small dollar and be easy to spin up or down.
Like a pencil spinning along its length.
Yeah, but an object with the same mass spread far out, like a dumbbell held wide.
Will have a huge dollars and be much harder to rotate.
Exactly. The geometry of the mass distribution is key.
Okay, so level dollar equals I omega. Now connect this back to conservation.
Perfect example. Feynman describes a setup, you can picture it, maybe a spinning rod with masses dollars on it, and some smaller masses dollar that can be pulled inwards along the rod by strings.
Okay, so it's spinning.
It's spinning with some initial angular velocity omega-1 and has some initial moment of inertia I luller. So its angular momentum is Levy-Luller I lulled 1 omega I11 over 1/8. Assume no external torque, like friction.
Right, so little r must stay constant.
Now, someone pulls the internal strings, drawing those smaller masses not all are closer to the center axis of rotation.
That reduces their distance, though.
Drastically reduces their contribution to the moment of inertia because of the $2 term. So the total moment of inertia of the system, I luller, decreases. Let's call it I42.
So I dollars is smaller than I dollars, but I dollars has to stay the same.
Right. Since I luller must remain constant, if I luller gets smaller, I lower that dollar, then omega must get bigger to compensate. The object has to spin faster, omega $1.
Wow. Pulling the mass in makes it spin faster, like the classic figure skater example.
Exactly like the figure skater pulling their arms in. They reduce their moment of inertia and their angular velocity shoots up, conserving angular momentum. It's a beautiful, direct demonstration of Iloweto and the conservation law working together.
That really ties it all together. Okay, so let's try and recap the main journey here.
Sounds good.
We started with complicated objects, things that aren't just points. And Feynman gave us tools to simplify.
First, the center of mass, $3. Its motion depends only on external forces, letting us separate translation from rotation.
Right. Then, for the rotation part, we needed new language. Angular velocity omega, angular acceleration alpha.
And the key dynamic concepts, torque, caut, the rotational force or twist.
Which depends on the force and where it's applied. The lever arm idea.
And angular momentum, the rotational momentum.
Linked by the fundamental law, tau is dLdtt, the rotational version of c del ddt.
And from that, the crucial conservation law. If external torque is 0, total angular momentum is constant.
Which explains things like Kepler's laws.
And then for rigid bodies, we found that low dollar is space I omega.
Where $1, the moment of inertia, captures how mass distribution resists changes in rotation. Someday, right, too.
That's the core framework. It shows rotational mechanics isn't really new physics. It's Newton's laws applied carefully to extended objects using the right geometric language.
And understanding in any dollar how the shape and spread of mass affects spinning. That's essential for analyzing pretty much anything that turns.
From tiny molecules to spinning planets to entire galaxies, the principles are the same.
It really provides a powerful lens for looking at the physical world. We hope this deep dive into Feynman's approach in Chapter 18 helps you connect those rotational dots.
Yeah, hopefully bring some clarity to these fundamental concepts.
Thanks for joining us on this exploration.